Welcome back to Lesson 13 in our study of the application layer of the TCP/IP model in the course Networks and Distributed Systems, based on the text Computer Networking, a Top-Down Approach by Jim Koros and Keith Ross. In the last lesson, we were talking about distributed hash tables. Did you happen to catch that I switched the key in the first example of the Social Security number and the name? It doesn't really make any difference as far as the information is concerned, but it struck me as a little bit confusing when I watched it again and then realized what I had done. But now we're going to continue with that discussion. In peer-to-peer systems, a peer can come and go without warning. Therefore, when designing a distributed hash table, we also must be concerned about maintaining the DHT overlay in the presence of such peer churn. To get a big picture understanding of how this could be accomplished, we'll once again look at the circular distributed hash table in Figure 227A. To handle peer churn, we will now require each peer to know the IP address of the first and second successors. For example, peer 4 now tracks both peer 5 and peer 8. We also require each peer to periodically verify that its two successors are alive by periodically sending ping messages to them and asking for responses. Let's consider how the DHT is maintained when a peer abruptly leaves. For example, suppose peer 5 in Figure 227A abruptly leaves. In this case, the two peers preceding the departed peer, peers 4 and 3, learn that 5 has departed, since it no longer responds to ping messages. Peers 4 and 3 then need to update their successor state information. Let's consider how peer 4 updates his state. Peer 4 replaces its first successor, which was peer 5, with its second successor, currently peer 8. Peer 4 then asks its new first successor, peer 8, for the identifier and IP address of its immediate successor, peer 10. Peer 4 then makes peer 10 its second successor. Having briefly addressed what has to be done when a peer leaves, let's now consider what happens when a peer wants to join the distributed hash table. Let's say a peer with the identifier 13 wants to join the DHT, and at the time of joining, it only knows about peer 1's existence in the decision hash table. Peer 13 would first send peer 1 a message saying what will be 13's predecessor and successor. This message gets forwarded through the DHT until it reaches peer 12, who realizes that it will be peer 13's predecessor and that its current successor, peer 15, will become peer 13's successor. Next, peer 12 sends this predecessor and successor information to peer 13. Peer 13 can now join the distributed hash table by making peer 15 its successor and by notifying peer 12 that it should change its immediate successor to 13. Distributed hash tables have been finding widespread use in practice. For example, BitTorrent uses the Kademlia distributed hash table to create a distributed tracker. In BitTorrent, the key is the torrent identifier, and the value is the IP address of all the peers currently participating in the torrent. In this manner, by querying the distributed hash table with a torrent identifier, a newly arriving BitTorrent peer can determine the peer that is responsible for tracking the peers in the torrent. After having found that peer, the arriving peer can query its list of other peers in the torrent. Let's talk about sockets. A network socket is an internal endpoint for sending and receiving data at a single node in a computer network. We discussed it quite a bit recently. It is a representation of this endpoint in networking software. Concretely, it is a representation of this endpoint in networking software, the protocol stack. Recall that a typical network application consists of pairs of programs, a client program and a server program, residing in two different end systems. When these two programs are executed, a client process and a server process are created, and these processes communicate with each other by reading from and writing to sockets. When creating a network application, it is necessary to write the code for both the client and the server programs. There are two types of network applications. One type is an implementation whose operation is specified in a protocol standard. Such an application is sometimes referred to as open, since the rules specifying the operation are known to all. For example, the client program could be an implementation of the client side of the FTP protocol. The server program could be an implementation of the FTP server protocol. If one developer writes code for the client program and another developer writes code for the server program, and both developers carefully follow the protocol, then the two programs will be able to interoperate. A web browser communicating with an Apache web server is an example of this kind of implementation. The other type of network application is a proprietary network application. In this case, the client and the server programs employ an application protocol that does not comply with an established standard. A single developer or development team creates both the client and the server programs, and the developer has complete control over what goes on in the code. Because the code does not implement an open protocol, other independent developers will not be able to develop code that interoperates with the application. During the development phase, one of the first decisions the developer must make is whether the application is to run over TCP or UDP. Remember, TCP is connection oriented and provides a reliable byte stream channel through which the data flows between the two end systems. UDP is connectionless and sends independent packets of data from one end system to the other without any guarantee about delivery. When a client or a server program implements a standard protocol, it should use the well-known port number associated with the protocol. The way HTTP uses, 80, and FTP uses 20 and 21, and so on. If not using a standard protocol, then the developer must be careful to avoid using those well-known port numbers. Remember from our previous discussions that processes running on different machines communicate with each other by sending messages into sockets. The application resides on one side of the socket and the transport layer protocol resides on the other side of the socket. The application developer has control of the application layer side of the socket, but little control of the transport layer side. Now let's take a closer look at the interaction between two communicating processes that use UDP sockets. Before the sending process can push the packet of data out the socket door when using UDP, it must first attach a destination address to the packet. After the packet passes through the sender's socket, the Internet will use this destination address to route the packet through the Internet to the socket in the receiving process. When the packet arrives at the receiving socket, the receiving process will retrieve the packet through the socket and then inspect the packet's contents and take appropriate action. So what goes into the destination address that is attached to the packet? The destination host IP address is part of the destination address. By including the destination IP address in the packet, the routers in the internet will be able to route the packet to the destination host. But because a host may be running many network application processes, each with one or more sockets, it is also necessary to identify the specific socket in the destination host. When a socket is created, an identifier called a port number is assigned to it. So the packet's destination address also includes the socket's port number. Therefore, the sending process attaches a destination address to the packet, which consists of the destination host's IP address and the destination socket's port number. Shortly, we will see that the sender's source address, consisting of the IP address of the source host and the port number of the source socket, are also attached to the packet. However, attaching the source address to the packet is typically not done by UDP application code. Instead, it is automatically done by the underlying operating system. See how this simple client-server application demonstrates socket programming for both UDP and TCP? Client reads a line of characters from its keyboard and sends the data to the server. The server receives the data and converts the characters to uppercase. The server sends the modified data to the character. The client receives the modified data and displays the line on the screen. You know, that's a pretty good lesson. Why don't we stop here and review what we've seen or discussed or explored in this lesson. Take care of any assignments that we may have. And when you are ready, come on back for the next in the series of lessons on the application layer.